Hello, everyone. Thank you for being here for my talk. Today, I'm going to talk about an area which is often overlooked in the domain of computer security, which is the privacy. My name is Simon Wicky. I'm a research engineer in technology. So, today, we're going to briefly talk about privacy on the internet, about anonymous communication systems, about the NIM network, about website fingerprinting, which is an attack on anonymous communication systems, and last but not least, the results of our ongoing research that we're currently doing. So first, what happens when you talk on the internet? Well, if you want to send a message like this guy here, you can send it in plain text through the internet. But then what happens? Everyone on the internet can see you. It could be your ISP, could be your boss, could be intelligence agency. Basically, anybody can see what you're doing. So that's not really good, right? So you could encrypt your communication and then problem solved, right? That's not exactly the case. Even though everyone cannot read what you're sending, everyone can still see what we call the metadata. Basically, everything about the communication which is not the content. The timing, when you send it, the location, your identities, who you are, your IP address, how many, the volume of what you're sending, if you're sending like a huge file or a simple text message, or from what device do you send it. And as soon as these informations are available, these guys are back. So I'm going to slow down on this slide to highlight two main problems. The first one is the privacy and anonymity in the what we call the network layer. So basically, those metadata. And I'm going to give you like a simple example in the context of instant messaging. How could you guess a person's birthday without even reading the text? Just think about it for a bit. Now, what's the only day of a year, like where on average you will get a lot more messages from a lot more people than the rest? And this day repeats every year. That's probably your birthday. And the next problem is that we also have a problem of privacy at the application layer. Basically, if this guy here wants to buy a book, and maybe he's a student and he wants a student discount, he'll have to prove to the seller that who he is, his name, like I'm Simon Wicky, I'm a student, I don't know, EPFL, and here's my ID and everything. It should be, and it could be easier than this. And that's where NIM comes into play. Basically, we're building an infrastructure that aims to solve these two problems. So the network layer, privacy, and the application layer, privacy. More on that later. First, I need to go through some definitions with you. So first, an interesting quote from one of the people working at Tor is, "Anonymity loves company. You cannot be anonymous if you're alone. Picture yourself, you can be like as much camouflage that you want. If you're on an empty square, you will be seen. You have to be in a crowd surrounded by people. And this crowd, we call it the anonymity set. So in that case, we would have sender anonymity. The receiver of the message cannot determine who is the sender. He might have a guess, like in that case, it may be one of the three people, but he cannot know more. This is the size of the anonymity set. That's the same thing for the receiver anonymity. The sender does not know who will receive the message. Now, don't get me wrong, he will know that the message will go to the right person. He just doesn't know where this person is on the internet. And last but not least, what's called unobservability, which is a third party would not even be able to tell that a communication is happening between two persons. Now, I'm going to introduce some protagonists for today. First, we have the global passive adversary, which is, as its name suggests, global and passive. So global in the sense that he can observe basically every link in the network, in any network, and he's passive as well. So he won't be able to inject traffic, to drop traffic, to modify traffic, only observe the traffic. Next up, we have the local passive adversary, which could be, like, for example, your not so friendly ISP. It's the same passive adversary. He cannot drop packets, modify packets, or inject traffic. He can only look, and he's located on only one point in the network. That's the difference between the global passive adversary and the local passive adversary. And the last one, we have Frank, which is our honest user who just wants to go web browsing without being tracked. Now, what about VPNs? You probably everyone in this room have heard of VPN. And it's fairly popular and advertised, like in a lot of YouTube videos. So basically, how do they work? So we have Frank that wants to visit a website. So he first encrypts his communication and goes to a VPN provider, who then forwards his request to the website. Now, there's a couple problems in this system. First, we have a single point of failure, which is not that good. I mean, the VPN could be malicious, so it could be compromised, basically not good. Then you could have a global passive adversary that could observe the link between Frank and the VPN and the website, and basically do correlation in the traffic. You could see, like, picture yourself a highway with a tunnel in between. The tunnel is the VPN. But if you see each car in this highway is the same color, same brand. They enter the tunnel black, they come out, I don't know, yellow, because there's a decryption process in the VPN. Well, basically, if you see like 3 cars coming really close, and they are alone, and then you see the same 3 cars, well, they will be yellow, but you see 3 cars really close together after the tunnel, they are probably the same. And even if the VPN provider is not malicious, he can still see everything you're doing. Like, he sees the full communication. He can know that Franks go to this particular website. Now, what about Tor? Just raise your hands in the crowd, those who know about Tor. Yeah, that's almost everyone. So basically, Tor is a network run by volunteers with over 6,000 nodes. 2 million daily users are using it, and really important, the threat model does not include the global passive adversary. So just quick reminder how it works. You still have Franks, you still have his not shady website, not at all. And you have the cloud in between. So there are a couple of onion nodes in between. He's going to pick 3 of them, the guard, the middle, and the exit. And these 3 nodes will forward the whole communication. Now, it's better than the VPN because we'll see in a minute, as we have 3 nodes in the middle, no nodes will be able to see the full path. So first he sends his traffic to the guard node. He will not send it in clear. He will first encrypt it with the public key of the last node, then the second node, and then the first node. It's what we call onion encryption. Then the first node will decrypt the traffic and forward it to the middle node, because he will have the instruction inside the layer of encryption. The middle node does the same, forward it to the last one. The last one does the same and forwards the requests to the website and back. When we have there what we call a circuit, and this circuit will stay the same for the whole communication. Now, what about our other protagonists? Well, the ISP looks screwed because the traffic is encrypted. He cannot see what's happening outside. He's screwed, right? We'll see about that later. And the global passive adversary, now I know he's not in the threat model of Tor, but right now a global passive adversary is not that irrealistic. And he can still do correlation, the same way he could do on the VPN. Now, let me introduce you to NIM, the NIM infrastructure that we are building with the great help of Exoscale. At the center of it, we have a Mixnode, which is attempting to fix the network layer privacy problem. We also have gateway on each side to prevent users from using the Mixnode for free. It acts just as sort of guards from the network. Next, we have the validators and the blockchain who are there to provide information about the network, to provide credential to use the network, and also some what we called anonymous credential. Now remember the student discount case. It would be great if, for example, instead of disclosing every information about myself, where I study, like my student number, if I could have somehow some sort of card that says, okay, look, this is validly signed, I'm a student. And then the sellers, because they trust the signatures, say, okay, here's your student discount code. Well, that's exactly what these anonymous credentials are for. Now, I said a Mixnet. A Mixnet is composed of Mixnodes, to be precise. A Mixnode was invented by David Chaum in 1981, mainly for emails, and it works as follows. Message come in, they are transformed, message come out. I mean, it's trivial. Let's do that one more time. Message come out. Great. So the idea is that you take a certain number of messages in, then as soon as you reach a threshold, you cryptographically transform them, you reorder them in a manner that cannot be tracked, and you send them out. The main idea is that the timing correlation is now destroyed. You cannot link a message, an incoming message, with an outgoing one. And you now have a really clear anonymity set, which is the number of messages that are in the mix with your message. Actually, it's sent in a batch. Now, if we keep this design, we still have a single point of failure. So we can, and that's what David Chaum did. You change these mixes, and now as long as one of these mixes is honest, everything's fine. But there's still some problem. Now I'm going to address these problems. The first one, this design scales really poorly. I mean, if you chain these mixnets like this mixnode like this, basically if you have 1,000 users, they won't be able to support the load. You cannot scale your network like this. You will have a high end-to-end latency. Since you're relying on other people to hide yourself, you will have to wait for them. You don't know if they want to send an email at the same time as you. It could be like weeks later if there's not many people using the network. And also you still are limited in your anonymity set, since you're still limited by the number of messages that one Mixnode takes in, basically. So how can we address this? By using what we call a stratified topology. So basically 3 layers of Mixnodes, and each messages goes through one of them. And the difference with Tor is that even if in one communication, each message will take a different path, like this. To the gateway, to the first Mixnode, to the second one, to the third one might be the same, to the gateway, and then to Bob. Easy, right? Now, we still have some issue with that. Like, how are the packets formed? How does the Mixnode work? Because we still have the high end-to-end latency problem. We fixed the scalability, but we still have some problems that I mentioned earlier. So let's get to that. So first things first, we use the Sphinx packet format, which is a provably secure packet format that provides bitwise unlinkability. You cannot link two packets by their bit representation. It also provides integrity with the embedded integrity tag in the header. And it also allows us to provide what we call SERP, a single-use reply block. If you want to keep your sender anonymity, the guy receiving the message should know like where to respond. And basically, you can do this by just pre-computing a header like this for you and send it with the payload to the guy. And basically, it's like a postage paid stamp. Just take the stamp, put it on the envelope. You cannot read the address, but you are sure it will go to the right place. And we do onion encrypt everything, of course, so that each mixnet can decrypt forwards to the next mixnode. Sorry. And yeah, basically it works. The messages are different. No nodes can see the full path. It just works. I mean, now to tackle the problem of the end-to-end latency, we are introducing stop and go mixnode. So basically now you don't wait for a certain number of messages to arrive, you just delay them. Watch out, it's going to be fast. Did you catch it? Let's do that one more time. Look, that the messages are not waiting, they are just delayed. This way you are guaranteed to have like an upper bound on your end-to-end latency. And how does these delays work? It's what we call a Poisson Mixing. For those who don't speak French, there's a fish because Poisson means fish in French. And so basically it's the delays are exponentially distributed. That means that their leaving time in the mixnode will not depend on their arrival time. Basically, each time a message leaves a mixnode, it's basically a lottery. It's just you pick one at random inside among the messages that were already in the mixnode. It could be one that was just sent. It could be one that was sent maybe not years ago, but minutes ago. For example, it could be. It works. You have one message coming in, the second one, there's one message coming out. You don't know which one it was. Maybe you have a third message coming in and another message coming out. You still do not know which one it was. There's still one message in this mix, but you still do not know which one it was. It's with equal probability one of the three that were there before. And now we still have patterns to hide. Like here we have Alice that is talking on the internet. We have another user that is maybe talking a little bit less, and we have a user that maybe he does nothing. He's just idling. So basically, what we do is we inject cover traffic right after the client. So the client is this box there. They are on the same machine as the user. You cannot observe this part. That's really important. And basically, it works as a buffer mechanism. There's an event that triggers every now and then, and basically he looks into the buffer of real message. If there's a message that is ready, he just sends his message. If there's not, he sends a cover traffic. The cover traffic will loop back to the user. And that has as consequences that the traffic looks the same for the three users. And basically, maybe some of these packets are covered traffic, but you don't know it. Now, quick summary about the differences of NIM versus Tor. NIM is circuit-based routing. Every communication goes through the same circuit. NIM is packet-based routing. Every packet goes through a different circuit or different set of nodes. NIM hides communication patterns using covered traffic, and is supposed to be resistant to timing analysis due to the nature of the mixed nodes, when Tor is not. Now, NIM also has rewards for the nodes to encourage them to have a good quality of service, where Tor nodes are volunteer, basically. So now we have a system, we're going to attack it. So how does a website fingerprinting attack works? So basically, this is a kind of attack that can be mounted by an adversary with very limited capability. It could be your ISP, basically a local passive adversary. And the setup, in this case, what we call the closed world setup, is that the ISP is listening between Frank and the anonymous communication system, and Frank can go to a certain set of web pages. It could go on Netflix, it could go on Wikipedia, whatever. But this set is known in advance, as the goal of the local passive adversary is to determine on which website does he go. Now, since there's a closed world setup, there's obviously an open world setup. This one might be more realistic in maybe showing how censorship works. So basically, Frank can now go anywhere on the internet. But the not so friendly ISP, he's monitoring a certain set of web pages. And his goal now is to determine, does Frank go to a monitored web page or not? Like, do we need to shut down his communication, or is it okay? Now, a little bit of history of this attack. It started in 2002, by Andrew Hintz. He worked on an encrypted proxy, what we now call VPN. And this attack used the particularity of HTTP 1.0, which was that in a web page, each object had one connection. So basically what he would do is to count the number of packets of each connection. Like, you collect data, you go to various websites, just build a histogram of the connection you have and the number of packets in each connection, and build your data set, your training data set, if you want. And then collect your data on your targets and just build the same histogram, match it against your data sets, and voila, you have your attack. So let's see how this works. By putting up a fight. Round one, websites fingerprinting versus Tor. Fight. So, in 2011, Panchenko and et al. Proposed a paper. They reached 55% accuracy on the closed world and 73% accuracy on the open world, which is quite good, but it can do better. In 2018, Bat et al. Proposed another paper, which was based on a convolutional neural network that was made for image processing, but hey, it still works, right? And they reached a whopping 97.8% in closed worlds and 89.2% in open worlds. That's scary. That's scary numbers right there. So results of the round, website fingerprinting win. Now moving on to round two, website fingerprinting versus Mixnet fight. Well, we have a problem here. We do not have any results yet. Problem is that Mixnets as of today are not optimized or were not made for low latency app. Like I said, with the Charmian Mixnet, you have high end-to-end latency. You cannot realistically go web browsing. Well, now we can try it with NIM. Now, remember, it's still not optimized for websites browsing. It works, but it's not optimized. And as long as it works, somebody will do it. So we might better know how it works. So we first need to capture some data. So here's how it works. We have our Mixnet. We have a gateway on both ends of the Mixnet. Then we have a Firefox who's hooked to a NIM SOX5 proxy to transmit the traffics to the gateway. And on the other side, we have a NIM client with a NIM requester, which is the component that does the request for us in the World Wide Web. And we have the capture point right here, which would be a capture point, a realistic capture point for a local passive adversary, an ISP, for example. Now, what we did, we took a URL list from Panchenko et al., the same Panchenko that did the paper in 2011. And so we crawled through almost 700 websites 40 times. That's a lot of websites. And that's our foreground. That's our monitored set of web pages in the open world, and that's also our closed world. For the background, we went through 100K web pages to represent like the background, the rest of the internet. We extracted various features and we fed it into a random forest, which is a machine learning algorithm. More on that later. Now, the features that we extracted are based on metadata. Basically, like you can see in blue, we have features that are related to the inter-packet timing. When we see, like, is it a long time between two packets? Is it a short time between two packets? Based on the packet timing, did the communication take long? Did it not? On the number of packets, basically a whole lot of features that we could extract from our capture data. And already now, you can see the difference visually between two websites. In blue, we have an example of a YouTube page. In orange, it's the features of another page. So even now, even visually, you can tell that only based on the metadata, these two web pages are different. So now that we have features within a machine learning algorithm, this one is called the random forest, because it's not technically a real forest. It's still a forest, but it is random though. So as probably everyone knows, forest is made of tree. In our case, decision tree. So let's say that I'm trying to determine if what is it that is flying in the sky. Well, maybe it's human. Who knows? In that case, yes, maybe it's Superman. Maybe it's not human, so it could be big or it could be not. If it's not, maybe it's a bird. If it is, maybe it's a plane. So basically, that's really basic, and that's how a decision tree works. So now a forest is made of trees, like I said. You have many trees, in that case 4, and you can, at the end, each trees will give you a class. You can take the majority, and it's done. I mean, it could be as simple as that. Unless the trees are big. Like you see this thin line on the top, this is an actual tree of one of our algorithms. And there are 500 of them. Can do a little close-up on that. So that's our tree, at least a part of our tree. And each box is a node. Each arrow is a question asked to one of the features. And basically, when you reach a leaf, you know in which class you are. So quick summary: it's a number of decision trees. It's a majority vote. You can take a majority votes at the end. And it's a multi-class algorithm. You are not limited to 2 classes, as some algorithms are. Now, I'm not done with the trees yet, because the first part works for the closed world, and we're going to use that for the closed world. For the open world, we're going to add a little bit of spice on top, and that spice is called a KNN layer. So to have a KNN layer, it means K nearest neighbors. You have to have a fingerprint. So instead of just taking the majority, you're going to pick the leaf index on which leaf it landed. So in that case, the first one gives 3, the second one is 4, etc., etc. Now you also need a distance. We're going to use the Hamming distance, basically number of different values between two lists. In that case, the 2 and the 1s are different, the 3 and the 5, the 8 and the 1, we have a Hamming distance of 3. That's pretty easy. Now, so basically what you're going to do is, when you have a test instance, you're going to look at the classification of some of the closest neighbor using the Hamming distance, and if they all are foreground samples, just says, okay, I'm testing a foreground sample. If they are not, just says that it's a background sample. And you can tune the number of neighbors k to adjust if you want like more false positive or more false negative. And basically we're doing it that way because we have way more background samples, so it should be it is a major point if it's a foreground. It's important. So now we're coming to the actual results. How does NIM compare to Tor? So we have NIM on the left, Tor on the right. In the closed world, we scored what we call the attack effectiveness. Basically, 0 is a really bad attack, 1 is a really good attack. So from a network perspective, the closest to 0, the better. So basically for Tor in the closed world, we were at 0.5, and for NIM we were at 0.1, which is much better. Now, remember, Tor is really made for web browsing. NIM just barely works with with web browsing. It works. It's not optimized for that. And the open world, again, Tor is around 0.5. NIM is a little bit higher at 0.28, but we're still lower than Tor. Now, those results are all fancy and that, but what do they mean? I mean, how can we interpret this? Well, the good thing is that with a random forest, we actually can, using feature analysis. Basically, at each step of the decision tree, one feature will be picked, and a decision will be made on that features. Now, if the feature did split the dataset really well, it will become more important. So we can graph this feature importance. Again, we have NIM on the left, Tor on the right. You can see overall that the Tor features, the first group of features is a little bit higher, where NIM, it's more like everything is more squished down. Everything should add up to 1, so it's normal that some of the features in NIM are higher in Tor. I mean, it looks more flat than Tor. Now what? We have our results, we have analysis. It's still preliminary results. This is an ongoing research, but still, we can maybe try other cover traffic parameters. We can try to compute the overhead cost. We can try with a different cover traffic strategy. And then we can try to improve the resistance of the network. So we're coming to the end of this talk. Basically, the takeaways are, it is important to have privacy on the internet, so we need to have an anonymous communication system in place. Website fingerprinting attack is a real threat on this communication system. And right now, NIM's Mixnet looks more resilient than Tor. Now, once again, thanks to Exascale to helping us set up this endeavor. If you want to ask a question, you can do it now or contact me by email or on Twitter. Thank you.
Thank you, Simon. That was an awesome talk. Are there any questions for him?
Okay. I start, he has one, then I have another one. So just first question. So you said that it is not very useful yet for low latency applications. So what is the current use case that you are saying NIM is much better than everything else?
Yeah, so right now NIM is maybe not optimized, but it does work with low latency app. The main usage would be like mail, maybe instant messaging, cryptocurrency transaction, all this kind of communication that are that do have a low latency requirement, but maybe are not that big.
So something like Zoom would not work.
It might be hard to have a Zoom call on NIM right now, yeah.
Okay, and what is if I want to surf the web with NIM? Tor is sometimes already a little bit slow because you have to wait for 800 milliseconds to have your page. What is it with NIM?
It will be higher, but you can imagine like some sort of setup where you would maybe on the mornings set up some script to grab some news website because you're in a heavily censored country. And when we come back, just go through the pages that you download, some sort of web fetching and not web browsing. Okay. That could be a use case.
Hi, thanks for the talk. I have a question which is sort of two questions on the security guarantees. I was wondering, so the threat model that you consider is a global passive adversary.
Yep.
And I was wondering whether is it possible that you could maybe say if NIM gives some guarantees if we were to consider an active adversary?
Yeah, there are some kind of attack, active attack on the on Mixnode. One of the most famous could be like the N-1 attack. Basically, just think of the batches in the Charmian Mixnet. If the attacker controls every one of them but one, and the one is the target messages, when they come out, the attacker will be able to spot, okay, this is not my message, this is one from the target. And this kind of attack is countered by the cover traffic as well. Because then the attacker cannot be in control of any messages but one. There is cover traffic.
Yeah. So my second question, or sort of the follow-up on this, will be on the Mixnet. I wasn't sure, but do you actually provide any verifiability of the functionality of the Mixnet? As in, so my thinking would be, as a user, for example, I may want to know whether NIM is actually sort of doing what it should be doing, and it's not the passive adversary that it should be protecting against.
The code is open source.
Yeah.
So basically you can verify on that. And the idea is that we are not running the nodes of the Mixnet. People are running the node of the Mixnet.
I guess the question is more like on the cryptographic side. So I guess you're not like maybe providing a zero knowledge proof because that would probably make it super slow, or...
Yeah, we'll do you for the cryptographic side. We have the Sphinx packet that is probably secure, and like I said, the code is open source, so you can check that we are doing what we say we are doing.
Okay, yeah, thank you.
I have another question.
Yeah, go ahead.
Sorry. So still usability, you said there's chaff traffic, so the thing is always sending. So if I want to use it with a mobile device, it will be using up my data plan. Is that correct? Or
if you have your thing on, yeah, but you could see it like some sort of VPN that you would fire up when you want to use it. Then you lose the unobservability side of the idea of the cover traffic, but you have to pay a price somewhere. There's no free lunch.
Cool, thanks.
Any more questions?
Thank you. Thank you for the talk. My question is regarding the cover traffic. So I understood how cover traffic is generated from the sender's perspective. But what I'm wondering is when we send real packets, right, to an entity, we might receive something, right? And thus, do we have cover traffic from the entities that we're sending data to? Because maybe there could be some correlation between, like, if we see packets coming back to our initial user, then I mean that could mean that it's no longer cover traffic, right? Yeah,
the cover traffic is every user generates cover traffic. So basically, the guy you're sending messages to will be generating cover traffic. So your messages will be covered by his cover traffic. Does that answer your question?
Sort of, but what I'm wondering is what if we see messages coming back, right?
Coming back to you.
Coming back to us. That means that essentially it wasn't cover traffic at this point, right? Or do we have cover traffic that also goes back to like users and then just gets ignored?
Well, technically you're sending like one message to one guy and then he's going to answer back. And so that will fill your hole. The hole that you had in the loop coming back. Does that answer your question? No?
Oh, it's more like, do we receive cover traffic?
Well, yeah, our cover traffic comes back to us.
Okay.
That's the idea of the loop.
Okay. Oh, okay.
Yeah.
Okay. Thank you.
It's like you're sending a message to yourself, basically.
Okay, awesome.
Thank you for the talk. I have a question. If I want to connect to one of the 9 nodes, how do I know the address? Who maintain a directory, or how does it work?
Yeah, the address would be published in the blockchain to have a decentralized fashion where you Tor does have some directory, but you have to connect to one of them and retrieve your address. There you have the blockchain. It's public. You can ask the validators. There are many of them. Everything works in a decentralized fashion.
And how do I know the address of the nodes of the blockchain?
Well, you just ask the validators. I mean, there will be a set of validators for the network that will be publicly available, and then they will provide every information you need to have a gateway, and then to forward your traffic in the Mixnet.
Okay. And second question, you show us how the message go from the client to the server, but how does it work for the message to come back from the server to the client? How does he know how it is routed back to the client?
Yeah. So right now, the idea is to use SERB. So like I said, it's like your computed header from the Sphinx packet. You just send it along with the payload, and he just used it to send back. Now, in the version that we used, to allowing multiple responses, so in the version that we used to run this attack, we just give the IP address to the other NIM client so he knows where to send back. But the end idea is to use SERBs.
Okay, thank you.
Was there any more questions? Thanks.
Thanks for the presentation. I have a question. You mentioned that the node have a kickback. They have their recompense. They have a gift.
A reward, yeah.
Reward, thanks. What kind of reward is that for them running in the network? What can you offer to them?
We do have tokens in the blockchain that can be later used to access the network.
Okay.
And so we have proof. The nodes can generate proof that they actually did good work, and they will get a small amount of token as rewards to cover the cost of the server and everything.
So they get to use the traffic for the network for free, right?
They do get token to then use the network. Yeah.
Okay.
Any last questions? Thanks again, Simon. Please give him another round of applause.